Welcome to December's Leetcode challenge. Today's problem is largest rectangle in histogram. Given n non-negative integers representing the histogram's bar height, where the width of each bar is 1, find the area of the largest rectangle in the histogram. Here's some visualization here. We can see the largest rectangle is going to be an area of 10 between arrays 2 and 3 with a height of 5 and a width of 2. So this is pretty similar to the water container problem, but let's see how we might solve this. Now, the very first approach we might do, the naive approach, would be to find every possible subarray and just calculate the areas for each one and then just return the max. We can do that in a nested for loop. It wouldn't be too hard. We can just get the length of heights right here, store the max equal to 0, and we'll just say for I in range of n, that's starting, and for j in range of I to n. Let's just calculate the height, which is going to be the minimum between heights from I to j plus 1, and the width, which is just going to be j minus I. And I think we'll actually need to add one there. Yes, so if having that, we can just calculate store the max between the max that we have so far and the height times width, and return the max. So this should totally work, and it does, but it is a time complexity of n to the 2 power n squared. And obviously we want to do better than that. This would reach a time limit exception. So could we find a O of n solution somehow? Well, okay, let's think about this. If you recall with the water container problem, that solution was using 2 pointers. And that worked because all we cared about was the outside bars, like say we started at 2 and 3. All we need to store was the minimum between these two. But that's not going to work here, right? Because with this problem, we actually care about what the minimum is with in between this array. So we'd have to check the whole between 2 and 3 to find the minimum of 1 and then calculate that. And so that wouldn't work. That ends up becoming an n squared solution again. So it wouldn't be any more efficient. So what else can we do? Well, what about a DP solution or a greedy solution? Again, with this problem, it's kind of difficult to do that because we need to figure out what is the minimum for each subarray. So even if we went with DP, we would have to have like a 2D array, which really doesn't work because that just ends up becoming n squared again. So really all we're really left with here is some sort of sliding window technique or using a stack. Now how can we do that? Well, here is the key insight. Say that we had an array that looks something like, I don't know, 10, 20, 30, 40, with the index numbers being stored here. How would we calculate the maximum area for this? Well, if it was like in increasing order like this, it would be fairly easy, right? We can just start at the very end and pop this off. We'll say, all right, pop off 40 and take our index number of 3, and the width of this would be what, 4. So just subtract 4, whoops, take 4 minus the index number, which is going to be 3. So this is going to be the width, and this will be the minimum height, right? So this would be 40. Next, we could take off this 30 here, and this would be 30, and then get 2. So this would be 60, right? And same thing right here. We just take 20 and pop this off here, and then this would be what? 3, so it'd be 60 again, and so on and so forth. And this actually is O of n. And this works because if we had it all in an increasing order, we don't really care about these subarrays because like this area here, we know that this is going to be greater no matter what, right? Like 2, 20, 30, this will be greater in terms of, I'm sorry, what I mean by that is it'll be greater in that the width is always going to be longer. And if we have so say we start with 10, the only one we need to calculate is from 10 all the way to the end here, right? Because 10 to 30 is going to be smaller than 10 to 40, since we know that 10 is going to be the minimum, we could just go all the way to the end. So that's going to be our intuition with this increasing stack. If we just store our information in the stack, then we can just calculate the ones that really matter, and everything else we could ignore. So how would we start? Well, what we'll do is we'll have a stack as well as the max height. Then we're going to have a for loop, and we will pop off from our stack in a while loop and calculate the widths and heights using the index number that pops off from this for loop here. So we need to have the index number as well as whatever height that we're pulling off in the for loop. Once we have that, then we can store our max and append to our stack here. And finally, just return whatever is our max, right? Okay, so hopefully this will start making sense as I code it out. So we'll have an empty stack first, as well as the max height or the max area being 0. And we're going to have a for loop. We'll say for the index number as well as the height in, we can just do an enumerate with the heights. And we'll have to have a while loop here. And what we want to do is create our stack to be increasing, right? So while there is a stack and, let's see, while there's a stack and the last item on our stack is greater than the height that we pop off or that we're iterating on. If that's the case, then we want to pop off of our increasing stack because we know it's no longer increasing. So what do? Well, let's see. First we want to get the width, or no. We want to get the height, which is going to be equal to whatever we pop off here. So we'll get heights, and we'll pop off from our stack the rightmost index. Now our width is going to be equal to, well, it depends. It depends on whether we have a stack or not. If we do have a stack, well, I should say if there is no stack, then we know we want to go all the way to the end, right? So the width is going to be equal to the index number that we're on, because it'll just span the entire width. Otherwise, if there is still a stack left, then the width is just going to be equal to I minus whatever is last on this stack. And we actually need to subtract 1 as well to get the width correct, since these are index numbers. So we popped off our while loop, calculated the width and height, and now we want to store our max, right? So just get our max here to be equal to max equals max between max and height times width. And finally, we want to add to our stack whatever height, or I should say index number, that we just calculated. Now, one thing to note is once we have gone through our entire array, we might have a stack here that's just completely just increasing. And that's not enough because we still need to calculate this increasing stack. So to do that, we could write another while loop here, or all we need to do is actually just add a 0 at the end, since we know that 0 will be the absolute minimum. So we just put it to the end, so that way we'll calculate every single area. And that would be it. We just return our max after that. So let's see if this works. Does look like it's working. Let's submit that. And there we go, accepted. So this is a sliding window technique with an increasing stack. Sliding windows are very popular questions in interviews. So it's something that I need to brush up on myself because they're very useful, but they're hard to come up with on the spot. So I might eventually make a series about that. I should definitely solve more of these sort of problems. All right, that's it. So thanks for watching my channel. And remember, do not trust me. I know nothing.